So I gave you now a description of the state space, which remember can correspond to a collection of possible environments and corresponds to the configurations or positions and orientations of the robot within those environments. Well, the next thing I want to do is what I call placing bodies into the environment. So I want to have descriptions of models where I can put something into the environment, and you can first imagine that a body is a robot if you want, but it's going to be more than that, and I'll explain that in a little bit. So each body could have a configuration space so that we transform it, right? So it's possible that a body could move around. It's possible that a body could be stationary. And I just want to be able to talk about these sets of bodies that are somehow not exactly the environment. They exist in the environment, and they can possibly move. I think here I'm going to assume in this tutorial that, that the body is a point, but be careful, even if it's a point, it still has an orientation. So even for a point, the point may be facing in some direction, because that's the way it is for a robot. Right? The robot is positioned in some way that it will be facing north perhaps, or south, some direction like that. If you want though, the concepts I present also work for more general kinds of bodies. It's not really a problem. You just have to think in terms of the configuration space and use these configuration space ideas. You can look in chapter 4 of my book, for example, for configuration space obstacles, but I do not want to complicate these sensor ideas with configuration space obstacle ideas. Those are both kind of independent. You can mix them together if you want to make a harder problem, but I think it's fine to keep the problem as it is. Right? So what kind of bodies might we have? Well, in robotics literature, people use many different kinds of terms, and I just want kind of a unifying word that I can use in the mathematical descriptions of things, so I just call them a body. But people use different words in different contexts depending on what they're trying to do. And I decided to just kind of gather up as many words as I could find and say that instead of using these particular terms that we often use in the literature, I would rather talk about bodies in terms of their properties, their mathematical properties. But nevertheless, I want them to be specialized with these kinds of terms. So for example, we have a robot which carries sensors, can perform computations, and executes motion commands. We're going to have a landmark, which is a small body that is usually at a known location, right? Like the tower here in Tehran, right? You know, it's a landmark, right? You can see it from many places. You know its location. So just like a landmark. So robots often use landmarks. Maybe there's something called an object. Usually that's a body that can be detected and manipulated by a robot. It could be carried or dropped off at a location. If you've seen some online graph exploration algorithms or online maze searching algorithms, you may have seen the idea of a pebble. This is like a landmark that you carry in your pocket, and if you go exploring, maybe you're not sure if you came back to the same place again. Right? Imagine being lost in a cave. Right? So you carry this pebble and you put it down, and then when you come back and you see your pebble, you say, aha, I know something now. Right? So that's very important. So people talk about pebbles. There's papers called The Power of the Pebble. Right? So interesting things like this you may have seen in some theoretical computer science literature. A target. Maybe you're trying to follow someone with a camera. So you may think of a target. Obstacles, we've already talked about. We may have extra obstacles in addition to the environment. Some extra bodies that we call obstacles, that may be fine. Evaders, from pursuit evasion. It's another kind of body that moves around. I guess the pursuer could be like that too. Maybe the pursuer is a robot, I don't know. I think a treasure is an interesting one. You may have a body that's fixed in one place, but you're not sure where the location is, but you can only detect it when you're on top of it, right? So like a buried treasure, perhaps. You know, you can dig in some place, that's your sensor, and you find the treasure. Good for you. But otherwise, you cannot tell where the treasure is going to be. And another one is a tower. I think you may think about towers in terms of cell phone towers. Transmits a signal, and using field-based sensors, you may be able to infer something about it. It's like a special kind of landmark, perhaps, but it emits some signal. So these are common possibilities. I could easily go out and find hundreds of papers that use any one of these terms. And I just want to say that there's some bodies we put in the environment. And then I would like to classify bodies by properties, because we want to build up a family of mathematical models. So for example, here's the properties that I think are important. So are the bodies able to move? If so, that makes it different. I'm trying to make a taxonomy, if you like, of different types of bodies that people put in the environment so that we can then study families of different types of problems that we want to make filters for. Am I speaking clearly enough? Is that okay? Let me know when I get too fast, and I can turn down the speed a little bit. That's fine. In the U.S., I talk about 3 times faster than this, probably. So I get very excited and I go faster. So try to turn the knob back down. Maybe you can have a remote control maybe and like push the button down. Let's see. So one question is, can it move? The second question is, can we distinguish the bodies from each other? Like for example, in the idea I said of a pebble. Maybe I have a bag of pebbles and I put the multiple pebbles around. When I find a pebble, can I distinguish that from another pebble? Right? That's a very important question to ask for these kind of problems. So that's very important, distinguishable robots. So that changes everything, whether or not it's distinguishable. You could have partial distinguishability. I'll talk about that. And also interaction. Is it possible to interact with other bodies? Well, this never happens in Tehran, of course, because the drivers are amazing, right? They can move their cars arbitrarily with no collisions. I don't know how it happens. But how does the body interact with other bodies? That's another important question. All right. So let me talk about these body properties. So one of them is motion. Okay, the body could be static, right? Never moves. Like landmarks. Most landmarks are stationary. Obstacles, maybe at cell tower. Nobody moves the cell tower. Maybe they move. That's number 2. If they move, actually 2 and 3 both correspond to moving, but I want to make further subdivision inside of that to say maybe you have a predictable motion, like a rolling ball or a pendulum. Or maybe you have a very nice predictable robot. Usually not, but sometimes you have a nice predictable robot. And so I want to say that there's some equations of motion that describe how it moves. So we'll just say it moves, but it's predictable. The kind of most complicated kind is unpredictable motion, right? Like the evader when you're playing pursuit evasion, right? There's another issue that comes up if you get into planning. If you're just doing sensing and filtering, it doesn't matter. But when you get to planning, can the body be commanded to move, right? Do we control the body or not? Maybe I'm observing robots doing things, but maybe in the design of a sensing system, I don't get to control the robots. I just observe them. So that's always another issue that comes in with regard to the bodies. Can the system I'm designing or the analysis I'm doing, the algorithm I'm making, does it have control? Can it move the body or not? In pursuit evasion, you move the pursuer, but you do not move the evader. So that's an important extra sort of bit to think about. So that's property 1 broken down into some smaller categories. So again, I go back to these terms. People use all of these terms, but I want to really emphasize what it is about the bodies that are placed that's mathematically important, right? That's how I'm trying to get you to think. So that's why I just want to wash out the terms and call them all bodies, and then go back to the mathematical properties of them. Number 2, distinguishability, as I said. So if I put n bodies in the environment, oops, sorry, I'm breaking your floor. I'll be careful, sorry. Now there's a big hole. No, okay, let's see. So if I have n bodies, and I can then imagine that there's an equivalence relation on the collection of bodies, right? So that I can, maybe the equivalence relation could come from some mapping that I make, like a labeling, right? I could have a collection of bodies, and for each body I produce a label, right? Like for example, if the bodies are humans, I could say there are men and women. And then I could say inside of that I cannot distinguish, right? I could say all men look the same, all women look the same, but they look different from each other, right? So that would be possible labels. In fact, that's my example. Yes, men and women. So it could be the case at one limit that I can distinguish everybody, right, from each other. That's the highest level of distinguishability. At the lowest level, maybe they're all equivalent. All I know is that they're bodies. For example, all humans look equal. They don't really look equal, but they may be looking equal with regard to the sensors that we define and the way we reason about the problem. So it's very important to know that. This is something, I imply here that distinguishability is transitive, or indistinguishability is transitive. It might not be, actually, if you think about it carefully. There's examples you can make where it might not be so much. Like, let's say, maybe you could, what's a good example where transitivity might not work too well? It happens typically with classification. I mean, it may be that you can distinguish a it may be that, what's a good way to do this? So red and orange might be distinguishable from each other, but then you might have a color in the middle that's like orangish red. And so you might not be able to tell orangish red from orange, and you might not be able to tell orangish red from red, but you can certainly tell orange from red. So sometimes this kind of thing is not transitive, but I'm acting like it is here, so hopefully it's good enough. And different kinds of body interactions. So it could be the case that maybe a body blocks a sensor. Call that a sensor obstruction. So just like you have obstacles in motion planning or in pursuit evasion, you could also just have, oh, actually that happens in pursuit evasion, yeah, that's right. The obstacles block the sensor in visibility. But you could also have a motion obstruction. Actually, I don't know if you've thought about this before. Has anyone thought about the problems of, say, in visibility-based pursuit evasion, where you may have some obstacles that block the sensor, but you might be able to move right through those. Right? So you can have some obstacles that block the sensor and some obstacles that block the motion. Those could be two completely different collections, right? So that could lead to an interesting variety of problems to work on. Maybe in some of these sessions in the afternoon we could think about these. I don't know if you find it interesting, right? How does that happen? For example, I could be looking at glass walls, so I can see through them, right? So that's a sensor that blocks my motion, but it does not block the sensor. I can look through it, right? What would the other case look like? Let's see. I have a sensor obstruction, but I can go through it. Any ideas like that? How might that be? Maybe it looks like a, what's that? Yeah, like a fog or something, right? Yeah, so I can go through the fog, but I cannot see through it, right? Very good, yeah. So it's interesting to separate these. Finally, it could be the case that the way they interact could be through manipulation, right? Which I believe Frank will talk about later in the day, or at some point during the course. But it could be that one body can move another body. So they're allowed to interact in a very complicated way. That's sort of the most maybe interesting case, perhaps. But I'm not going to do too much with that. But I am interested in the first two quite a bit more. But I'm interested in maybe a body can move another body out of the way. Robots do this all the time. All right, and I'm going to allow a couple of more things here in my models. I will allow fields. So a field is a function, let's say, that maps Rn to Rm. And for our cases, n will be 2 or 3, and m will generally be less for the things we do. So for example, maybe I will just have a sensor that goes from, well, eventually, let's start a field. I just want to talk about, there could exist, I'm not talking about sensors yet, I'm sorry, but I just mean there are fields in the environment, right? How does the field look? Well, it looks like a needle diagram like this, and it just says that at every point in the environment, maybe I have a binary value, or maybe I have a real value, like an altitude map. Maybe I have, oh yeah, this one up here is interesting. It just tells 1 if there's an obstacle, or no, this is 1 if, oh, sorry, 1 if you're not in the obstacle region, and 0 if you are. So you can just use a field to just binary encode where the obstacles are. So fields are at least as powerful as describing where the walls are. You could have an altitude map. You just give a real value for every position. Or an intensity field could look like that. Or you might have an electromagnetic field. Maybe it gives a 2-dimensional vector at every place. Of course, in the real world, it gives a 3-dimensional vector at every place. Or if you're a physicist, it gives even more complicated things. We're also going to introduce time, and at different points in the tutorial. And I think time is, I'm going to imagine time to be some interval. Usually I just do not specify the final time, so it could be an open interval that goes off to infinity, but does not include infinity. And then I will define this kind of space here called the state-time space, which is just a Cartesian product of whatever state space I made with time added onto it. And so then I think of a z here, which is a pair. I'm sorry I had a z earlier on the slides. It's not the same thing here. But I mean that z is a pair, x comma t. It's saying the state at some time. A lot of people, when I start talking about state-time space, think that I'm going to talk about something cool like relativity. I'm not. I don't care about any kind of curvature of the space-time continuum here. I'm going to assume it's all perfectly, I'm going to assume that Einstein was wrong. Right? So just don't worry about that stuff. I'm just saying that there's a 3-dimensional or 2-dimensional space that the bodies move in, and sometimes we use the time axis, right, which is common in planning and lots of other computational geometry and kinetic data structures. People reason about the time axis, right, for example. So that's all I'm saying. There's this extra space that includes time. All right. I'm going to be talking about state trajectories, which look like this. It's a function that's a path, a time parameterized path, that goes through the state space. So in other words, it maps time to states. There's going to be two ways to look at that. I can look at that as a mapping into X. So there's a starting state and an ending state, perhaps, and then I have all these states along it. So that's the image of that function in the state space. I can also write it like this, which is more informative. If I go to Z space, remember Z is state cross time, and in that space, it looks like this. It makes a nice function, because I guess that's called the graph of the function, right? So I'm just plotting out the function here, and I can imagine now this particular subset here, which corresponds exactly to where I'm at various times, right? Where the state is at various times. And I can expand the state space by taking derivatives and all of that and make differential equations, but I'm not going to do that. I don't think it's going to be too interesting for us, but one can do that. But I just want to point out that sometimes it's helpful to look at the problem in Z space, let's say, instead of these X space or state space. And now I'm finally ready to define some sensor mappings, and these are going to be virtual sensors. And I'll give some of these, and then I'll probably continue tomorrow on my lecture on these things. I think I have more slides today than I have on any other day, probably, so I'll probably go through most of this, but not all of it today. So now let's say, suppose we have any physical state space, X, and we have any observation space, Y. I guess I just defined an observation space here. I'm just saying any set you want. I will call it Y, and let me call it observation space. Then I define my virtual sensor like this. And I'm going to use this H function over and over again until you're tired of it. So I will keep using it. X to Y, that's it. That corresponds exactly to what I had a few slides ago, right? When you were asking about, is it a many-to-one mapping? It's exactly a mapping like this. It's some function H. It goes from physical state space to an observation space. So, and it's a perfect mapping in this sense. There's no, it's not many-to-many or anything like that. So it can be many-to-one, and that will be very interesting. Remember when I talked about transfer functions? When I talked about physical sensors? This corresponds a lot to that, I would say. It looks like the transfer function that people talk about in the handbook of sensors. Now, when there's a state, X, I imagine that this model says that the sensor instantaneously observes Y. That's going to how it looks. X produces Y using the mapping H. So I want to give some examples of that. I'm going to give some basic examples, or what I like to call boring examples. And then I will give some that correspond more to different kinds of robotic situations. Okay? And the reason why I want to do this is so that I can define the kind of information, in terms of information states, that we want to give to filters. And remember that all these things I'm going to be defining are what I call virtual sensors that can have different kinds of physical implementations. I may remind you of their physical implementations as I go, but I'll forget for some of them. Here's some basic examples. And these examples will become, I think, reasonably important in a little bit. Just to be kind of mathematically complete, it's nice to have sensors like this. Here's one called the dummy sensor. Right? Imagine you go out and buy this sensor, pretty nice one. It produces the same observation regardless of the state. Right? Would you like to have one of those? Right? So not very useful, probably shouldn't cost very much. It just produces an output 0, let's say, all the time. Right? I'm going to refer to this one a little later in the talk. It'll be quite helpful, actually, to consider this one. It's like a special case. You know this. As computational geometers, you know that for most of you who are computational geometers, or even in math or wherever we go, there's always the special cases, right? The boundary cases. This one's a very important boundary case, and that's why it's included, the dummy sensor. Here's the other extreme. How about the identity sensor? It just goes poof and immediately gives you the state. Right? If it gives you the state, that's as powerful as you can get. There's going to be another collection of sensors that are almost as powerful. They're very, very close. And I will call them bijective sensors, which is that it's a bijective function, right? So if H is bijective, that means there exists an inverse so that I can construct X from Y. Now, if you think about computation, maybe computing this inverse might be difficult or impossible. So that's something you should keep in mind. But if it's not bijective, it's worse than that, right? So there's not even exist an inverse. So the state is not even theoretically reconstructible in the strongest, most abstract theoretical sense, right? You can't even do it if you do not have a bijection. So this is a special case of a bijection called the identity sensor. So that's two extremes. I can make linear sensors. I think it's nice to think about these. Maybe I have a matrix C that specifies the transformation from states to observations. I'm not going to do very much with those, but I think they're helpful to think about a little bit. So if C has full rank, then H is a bijective sensor. If it has lower rank, then there are lines or planes, or more generally hyperplanes if you have higher dimensions, but we don't here because we only have X being three-dimensional. Then you have lines or planes that produce the same observation. It's kind of interesting. That's what the ambiguity looks like. Linear sensors are well loved in control theory. Just everything that's linear works well in control theory. Right? Everything that's nonlinear, people just try to force it to be linear as much as possible. All right. Let's see. So basic examples. I'm now starting into more interesting kinds of examples. So, oh no, this is still a boring one. Yeah, basic examples. This one could say maybe the sensor just observes some components. Like for example, maybe I have a position sensor. The position sensor observes the position, but it does not tell you the orientation. Maybe I have a compass, an ideal compass. It tells you your orientation, but cannot tell you your position. So there's another nice symbol. I call them projection sensors. They just tell you exactly some of the coordinates by direct projection. So that one's actually less boring than the previous one. This can give you very useful information. It corresponds to virtual sensors that we use in robotics all the time. Again, this is like a catalog now that I'm going through. Imagine we're shopping for sensors. Right? We're just thinking about different kinds of virtual sensors that we can make. So going to the mall and going to different stores and picking them up. So here's a mathematical depth sensor. That's a very important family, depth sensors. I already showed an example like this. Observe the distance to the boundary of E. So I have the boundary of the environment, and the state space for this could look like a subset of, remember this is positions and orientations, and this is a set of possible environments. So that's how it looks for a very simple depth sensor. So here's how to specify one mathematically. So let's say the robot is a point, it's in a particular configuration, so position and orientation, and then based on that, I draw this, or I shoot this ray, let's say, called B of X. X encodes my position and orientation and environment, right? How much do I need for X here? Remember that X includes all of these. The position, the orientation, and exactly which environment we have. And it has to be that the position is in E, and E is in my fancy collection of possible environments. So all of this has to happen. So if I give you X, you have everything you need to predict what the sensor will observe. That's a very important concept that will happen again and again. When I give you the state, you have enough to predict what the sensor should observe. You don't have enough to reconstruct the state, but we can pretend we are like gods of some kind, and we can have the state to predict what the sensor is going to do. It does not mean that the sensor, the person using the sensor has that information, but if we make the mapping, we can pretend we have it. All right. So here's one of the most basic kinds. If I can put something into the physical implementation, this could correspond to some laser pointer with a simple camera that maybe observes the displacement. I can get a three-dimensional depth measurement. You can do it with sonars, many other kinds of things. So here's the idea. I have this sensor mapping, and it's a function of the state. The state here, I guess I've written it two different ways, but it includes position, orientation, and environment. So given those things, I just take the distance between the position and B of X, which is this point you hit on the wall there. Right? So wherever I hit, when I'm pointing in some position or orientation, I take the norm of that, I just look at the distance, right? The value there. And that will give me some measurement, right? Actually, I should have probably put another slide here. It's going to come later, but one of the things I really would like you to kind of think about as I go through these is, what's the set of possible states that produces the same measurement? Like for example, if I observe that the wall is 3 meters away, I can go like this and it's still 3 meters away, correct? But I can also get closer to the wall and rotate, and it's still 3 meters away. And I could be in different environments entirely, with the wall being 3 meters away. But even if I give you the environment, there's this interesting two-dimensional set, right, of configurations that give you the same measurement, which I think is kind of interesting. So This might imply that there's some interesting cell decompositions that could be done, which I can talk about in a little while. So I'm going to care a lot about those in a little while. All right. Here's another one, boundary distance sensor. It's kind of interesting that I can derive this from the sensor I just gave. I don't know if the notation makes too much. You don't have to remember too much of it really, and it's also in the tutorial paper that comes along with this. But boundary distance just might say how far away is the boundary. Right? So if I'm standing here, maybe the boundary is 1 meter away, right? I will give you a lot of trouble with the camera there. Sorry. Keep moving. So the boundary is 1 meter away. So this means out of all directions, what's the minimum, right? So that's why there's a min there. I'm just saying out of all directions, what's the minimum directional distance? So that's how far away the boundary is. That one's a little harder to implement in some ways, but there are reasonable sensors for that. Maybe I could have an array of sonars or use a much more powerful sensor, but it's essentially looking in all directions and taking the min. All right. So no dependency on theta. Proximity sensor. Maybe I have a binary sensor, so the outputs are 1 or 0. That's all I have. I get 1 or 0, and I get that only if I'm within a certain distance of the wall. So if the body is within a certain epsilon of the wall, I have the wall here, and the body's here, and if it's really close, maybe this is a threshold here, and this is some distance, epsilon. So if the body is here, I observe a 1 because I'm less than epsilon. If I'm outside here, I observe a 0. So proximity sensor, that can be derived from the previous sensor by just looking at the distance and then calculating this epsilon. However, you might not want to observe this by computation. You might want to observe this by just having a simpler sensor that can only tell you if you're within a certain distance or not, right? So it's a cheaper sensor. You could use the more powerful sensor to simulate it. This idea of simulating one sensor using another, I'm going to formulate and formalize later in this presentation. It'll probably be tomorrow for that. But I'm trying to give you a bunch of sensors so that we can then ask, how are these related? This will be a lot like comparing the power of different computation devices, like how much more powerful is a push-down automaton compared to a finite automaton? How much more powerful is a Turing machine? I want to think about how much more powerful is one sensor than another. And I think I can formalize this, but before I do that, I want to give you a lot of things to compare, right? Just like push-down automaton, regular automaton, there's non-deterministic automaton, and all different versions that people compare these, right? They show that some are equivalent and some are strictly more powerful. So I want to give you a lot of examples so that we can start to think like that. All right, so boundary sensor is very nice. Maybe I just boundary sensor is just a special case when epsilon is 0. So I just say, is the point on the boundary or not? That's very easy to implement with a contact sensor in a robot, right? It just goes click when the robot touches the wall. That one I don't care about. Shifted directional depth sensor just means I could have a sensor that measures the distance, but it's at a direction different from where I'm facing. So maybe there's a 90-degree difference here. The reason why I put that one here is so that I can define sensors now that measure depth in multiple directions. So for example, maybe I'm facing the wall, but I get 4 distances. I get the forward distance, the side distance, the behind distance, and the right distance. So I get now 4 numbers. So that's very reasonable. You could put 4 sonars or laser pointers on a robot and get 4 different depth measurements. So that's a possibility for that one. What I like is the limiting case, which is the omnidirectional depth sensor. And this starts to look very close to visibility, right? So in this case, imagine I can measure the distance in all directions simultaneously. What does the observation look like in this case? What's interesting in this case is that because you can measure in all directions simultaneously, and by all directions, I guess I really mean all, so that it looks like an infinite dimensional vector of observations. If I go back here, I get a 4-dimensional vector of observations, right, for that. So if I measure in all directions, it's the limiting case where I have a continuum of directions. And so by going in all directions, it looks like I have a function, right? An infinite dimensional vector space usually means a function space. And so I have a function that goes from S1, all directions, into real values that are non-negative. That's a really interesting object, right? The observations are functions entirely. So poof, I get an entire function. That's a very strong assumption, but yet we like to use it a lot. So how does that look, for example, to a robot? It might, when you plot the function, it may look something like this, right? When I sweep around, if the robot's in an environment like that, this is how it might look, right? That's how the data looks, by the way, for people who do laser range scanning with robots, or even if you use the Kinect, for example, this is how the non-colored part of the data looks, the depth part, right? That's how the environment may look to a robot with a powerful sensor that looks in all directions. And we can add some depth limits to it. We may say we have limited angle or maybe limited distance. So maybe we can only observe distances within some region. Very realistic for cameras, right? If you get too close or too far or outside of the field of view of the camera, you observe nothing. So, so this is a very important to add restrictions on these and make sensors for that. So it's important to relate these as well. All right, I'm going to talk about another class of sensors. Are there any questions? That's okay. This part's maybe a little dull. Perhaps I'm building up a catalog, but I want to hopefully give some ideas. I mean, imagine when we get to detection sensors next, you can imagine for pursuit evasion problems or other things like that, you can substitute in many different kinds of models like this, many different kinds of sensors and such. So the depth ones are probably used for giving you information about the map of the environment, right? Or localization. So those are the slam-like sensors. The detection ones, I think, are going to be closest to visibility-like sensors, I think, that many of you are familiar with. So let's talk about the detection sensor. So the idea is that each sensor has a field of view, or what we call a detection region. So I just drew them in yellow there. Some region in which you can detect bodies. Remember, we just had a general idea of bodies that go moving around. So maybe it could be like a beam. Here there's not enough, it's so thin that you can't see the yellow. You know, it's just a simple beam and the body can cross it. This looks like a camera pointing at the wall. This looks like an omnidirectional visibility sensor. This looks like you can detect within a disk. Now this is some strange blob that can even reach through the walls. I don't know, maybe it's like a radio signal detector. So detection sensors. So here's some fundamental questions about these as we try to categorize these different kinds of sensors. Can the sensor move? So maybe I can put my detection sensor on a robot and carry it around like a camera that sweeps around. That's how it looks in pursuit evasion. Or maybe the camera is fixed to the wall, right? So maybe it's just up in the corner and it observes all the time from the same position. Are the bodies so large relative to the range of the sensor? This is another important issue. Three fundamental questions. And the simplest case is when the answer is no to all three of these. So I just want to say that the easiest case is when the sensor does not move. Here's another question. Are the bodies so big relative to the sensor range that we really have to worry about the fact that the bodies are partially in and partially out of the sensor range? Is that important or not? Or is the body so small that it's like a point, and it's either in or out in a very simple way, right? So in other words, do we have to consider partially in and partially out? So that's kind of an important distinction. And another thing is, does the sensor additionally give us information that helps us to classify? Like maybe I say, oh, that's not only a body in the field of view, but it's a human, and it's a man. You know, maybe I know that much. So it could give additional information. Simplest case is no to all three of these. Let me give them the simplest case. So for example, I could have a static binary detector. It just tells whether or not the body is inside the sensor range. Is it in or is it out? Right? It's the easiest case. That reminds me a lot of this floor mat. Somebody is either stepping on the mat or not. That's all you get. Right? And the mat does not move, right? So it's stationary. This really does correspond to the case where the answer to all three of these is no. I don't care a body being partially on or partially off. As soon as they step on it, it works. It doesn't move. And there's no additional information that you get. So it's a very simple sensor like that. Maybe a sensor beam might be like that too, that you cross. I could have a moving binary detector. Maybe it tries to detect evaders or something. Like this, I just have a camera mounted on a robot. Right? So in this case, it gets a little more complicated because I use my state here. And I look at what do I have here? I have the configuration of the body that carries the sensor, and then I have the position of the position of the body in the environment. So that gets a little more complicated, right? It's like the way to imagine this is that I'm going to have the robot that carries the sensor. It's looking in some direction, and then there's the body here somewhere, right? So that's the body. I should have made a larger detection region. Oh, it's pointing this way. Let's make the detection region. Let me get some other color. So this is the maybe detection region that it has. All right. So there's some detection region here. That was my region V from before. And then the body is here. It's at some position P. And then the robot has some configuration Q. Right? So that's the idea here. When I put all of those pieces together, in order to get the state, I have to talk about both P and Q. Because the robot might be in some configuration, the body could be moving. And for these kind of problems, then to define the sensor, it's very simple detection, 0, 1. But I just have to point out that the state space now includes the configuration of the robot and the position of the body. So all of this stuff comes together. When moving, you have to consider configuration of the body that carries the sensor, and then the configuration, if you like, of the body that's being detected. So they both come together in some way. If you get up to the case of larger bodies, as I said, then you have this problem of you could be partially in or partially out of the sensor, right? The body could be partially in or partially out. That starts to look complicated, like obstacle regions in the configuration space. I'm not going to do very much with that in this tutorial, but I just want to point out that if you want to extend these models to consider complicated bodies that you're trying to detect, and you want to figure out if they're partially detectable or fully detected or not detected at all, then you may be stuck with these configuration space kinds of complications, because there's a configuration space implicitly in here due to the configuration of the robot. In fact, that might be interesting computational kinds of questions of pure sense to determine how much of the body is in or out. But I think they correspond very closely, though, or directly to robot obstacle kinds of computations, collision kinds of computations that we're familiar with. I can extend a little bit more. I can say that suppose we have n, that should be point bodies, n bodies that are points, and maybe I say that the detector will tell me if there's at least one body. So my state space is included now to have the configuration of a robot and then a bunch of points placed in the environment. So I now have a bunch of bodies, and I could have a P2 here and P1 and P3 and P4 and P5. So I have a bunch of bodies here, and then my sensor just tells me, yeah, there's at least one body that's in view. So that's a binary sensor that can tell you that. Maybe it counts the number of bodies. So this makes the state space a bit more complicated, because I might not know how many bodies there are a priori. It could be helpful, for example, at the shopping mall. I want to count how many people there are. Or maybe in analyzing wildlife, I want to count the numbers because I'm trying to study I don't know, environmental safety or something, and I'm trying to figure out whether or not the population is going up or down. I guess the state space gets a little weird for that, because it's like a Cartesian product of, I can imagine there's coordinates for each one of the bodies, but I don't know how many there are, so the state space gets a bit strange in that I have a union of Cartesian products that goes on indefinitely because I don't know how many bodies there are. But nevertheless, we can define such a big state space, and the sensor is very easy to define. It just says, well, how many of those bodies are in the visibility region, let's say, or detection region, V of Q. So it's just take the intersection and then take the number of them. I can make one with labels that do classification, as I said, that tell whether each body is a man, dog, tree, car, whatever you like, by using labels. All right, another family of sensors. I think I'm just going to be able to kind of mostly get through my sensor catalog today, and then I'll have to say more about how to build these up. The pre-images are the interesting parts, actually. Maybe I have to leave you in suspense for next time, I think, before I get to these. Relational sensors. This is an idea that Leo Gibas came up with in one of his papers. Very well-known computational geometry, obviously. The idea is that on a collection of bodies and doing that I want to sense, there's a relation. And so, relation in the ordinary sense. And so, for example, I may have a relation that says that a body is in front of another. Or maybe the relation is that the body is to the left of another. Right? The body is on top of another. And so I'm going to make some relation, let's say Rx, Ij, and it will mean that the body I is related in whatever sense we want to Bj when the collection of bodies is at state X. So these are it's a very helpful family actually to come up with. Let me give you an example. So I'll give you a few examples here. So first we start off, we define whatever relation we want, and then we just make a binary sensor that is true if it's satisfied and false otherwise, or in other words, just 1 and 0 if you like. I don't have to define logic formally here for that. And now, from this primitive, I try to form compound relational sensors. For example, using this relation to the left of, I can imagine there's a camera and there's a few bodies in the environment, a few points here if you like, and then I get an observation like 4, 2, 1, 3, 5, which just can be made by composing these primitive detection sensors, right? This is just telling me for each pair of bodies, is one to the left or the right of the other. If I can extract that information for all pairs of bodies, then I can give you a permutation, right? It's just telling what's the order of the bodies when they're in the field of view of the camera. If that were a camera, for example, that's doing the detection. But this information that I get from this sensor does not tell me the precise angles. I don't know what the angle is between them. I'm only saying that the sensor gives you the permutation. I think Leo Gibas was thinking like that as a computational geometer. That's the critical information, right? And if that permutation changes, that may mean something significant, right? So that's why there's this kind of model that he's thinking about in a different context, but I think this is a very broad family that's worth considering. So the observation space for this is just all 5 factorial permutations of these 5 bodies. If you have an omnidirectional sensor, oh, no, that's coming in a bit, yeah. Here's another one, sorry, a distance sensor. This one could say, okay, I use the relation is closer than, and then based on that, I get an ordering like this. I get a permutation that is, okay, 2 is the closest, then 5, then 3, then 4, then 1. What kind of sensor might give you information like this? Can you think of anything? Laser scanner could do that, that's right. So that's a very powerful sensor. So I could run a laser scanner and then take a sort. That's right, that's good. Any others? Sonar's good. Any more? Let's see. Vision's good. Here's one to think about. What if those are all cell phone towers? Right? Or Wi-Fi base stations, right? So then, that's right. So just look at the strength of the signal, and I get an ordering like this, right? So sometimes the tendency is to take a very powerful sensor, like a range scanner, right? The range scanner is like the universal simulator of all other sensors. It's like once you have range data for everything, you can build almost anything from it, right? But sometimes there's a counterintuitive solution, like maybe just the signal strength from Wi-Fi will give you this information, right? So it's very interesting to think about. That's why I want to talk about relationships between sensors and this neat thing called a sensor lattice, which will have to come next time. I started a few minutes late. I'm going to go just a few minutes over if it's okay, and then I'll be done for the day. So cyclic permutation sensor corresponds to the omnidirectional case. So maybe you have an omnidirectional camera, for example, and I get a cyclic ordering, but I don't care where that ordering starts. So this is the cyclic version of the left-right case. Here, right, is the left of. But in this case, it's kind of interesting. I have to think about cyclic permutations. Is that okay? Right? So if I go all the way around, there's no natural start. So you end up with this nice family of cyclic permutations. If I have only 2 points here, what happens? Yeah, but if it's a cyclic permutation, 2, 1, and 1, 2 are the same, right? So I need 3 of them before this even makes any sense, right? So if there's 3 points, I think there's 2 different cyclic permutations then. You have to think about that. So it's quite interesting. So if I lose the ability to determine, let's say, where the start is, right? There's like the start of the sweep and the end of the sweep. If I lose the ability to determine that, then it's a different space of permutations. It's something important to think about. There are these subtle changes. All right. Gap sensors. which are very closely related. But you know what I want to do, since I have a little bit of time for today, I think I'm going to jump ahead and give you a little bit of a taste of the pre-images. We're going through so many different sensors. I want to show you something that's coming a bit, and to give you kind of a taste of what's coming tomorrow. So let me skip over gap sensors and field sensors for a bit and say something about pre-images, which is why I'm giving you a lot of these. So here's what I like to think about. Given the sensor, look at this pre-image of the mapping. In other words, what's the set of all states that produces the same observation? I think this is a very helpful way to think about sensors, because that is the uncertainty that's being somehow brought in by the sensor observation. It's all states are equivalent somehow that the sensor is observing. I like to think of the sensor as a bread slicer. If the state space were a loaf of bread, right, probably the bread should look a little flatter here, right? But, you know, this is the puffy bread that we have in Europe and America for the most part. But you slice it into pieces. I like to think of it this way. So in other words, when someone gives a sensor, what we're talking about when H is given is a partition of the state space. That's how I think of a sensor. It's a partition of the state space. Right? And inside of each set in the partition here, these are all states that produce the same observation. So I want to try and encourage you, try to maybe sleep on that tonight. Think about how sensors are really just partitioning the state space. Right? If there are only two observations, then there are only two slices of bread, right? If there's if you have a range scanner that provides very accurate depth measurements, you're cutting the state space into a lot of little pieces because you're getting very accurate information. So I think it's very helpful to think about. And so I want to think about the partition of the state space that's induced by the sensor. And that's going to be very important for us in the next part of the lecture. For example, I gave the detection sensor already. So suppose I have this sensor that tells me how many bodies, points in this case, lie in some fixed detection region. Right? So the sensor can tell me. Imagine I tell you that there's, I don't know, what is this example? I have 4 bodies. Maybe I tell you there's 4 bodies. Okay? There are 4 bodies, and they move around a lot. But my detection region stays fixed. So it's like a camera that's fixed, and there's 4 people moving around. Sometimes they go in the camera view, sometimes they go out. If that's the case, then this is a kind of abstract description, maybe, of the 5 different possibilities. Is that right? Either all 4 of them are out, 1 is in, 2 are in, 3 are in, or 4 are in. It could be the case that these bodies are distinguishable initially. That's the way I defined it up there. But the sensor cannot tell, it just counts. And so the sensor is telling, well, there's 5 equivalence classes. So this is the way the state space, what would the state space be in this case? If there's 4 bodies, then the state space is RH, right? So X equals RH in this case. And the sensor is chopping RH into 5 pieces, right? So these are the slices of bread, if you like, right, for the state space. So that's what I want to do. I want to think about these kinds of slices that we get. Here's another example, which I think is really pretty. Let's suppose I put you in a known environment. So I give you some environment E and some states and some, I give you some environment E, and then the state space is the set of possible positions in E and orientations in S1. And so now, what are these pre-images? They are, let's say, regions or chunks of SE2, right? I told you this already. Like when I was standing here by the wall, I'm 3 meters away. What's the set of possible places? I have a question for you for the computational geometers who are in the audience. Is that an easy or a hard problem? If I give you a polygon, right? Is this kind of a known and reasonable thing? Let's think about this. Something to finish on maybe. So for example, if I give you a polygon, give you one of the weird ones or whatever. Right? Oh, that's bad. Okay. So I give you a polygon. And then I say, all right, in that polygon, I put a sensor, a directional depth sensor. That the directional depth sensor, so I'm somewhere in here, who knows, right? But the directional depth sensor said h of x equals 3, right? Can you compute the subset of SE3, right? So now I got to compute a subset. Let's just look at it as a subset of R2 cross S1 So there's some subset that's h1, that's the inverse of y, is some subset of R2 process 1, right? Is that hard to compute? H inverse of 3 here, I guess. I'm just using a particular example. What do you think? Yeah, right? I don't know. Is that easy to do? I don't know. In fact, what I would really like to have is I want to know what these are for all y. Right? So I give you input a polygon, and I want to know what these pre-images are for all values here. And I would like to know how they combinatorially change as a function of y. Has anyone thought of that problem before? I don't know. I've thought about it a little bit, but I wonder if I find that very interesting because that reveals a lot about the structure of the environment and tells me a lot about what I can do with regard to localization using a very simple sensor like this. So it's a very important structure, and I don't think people have, I don't know. I haven't seen it in computational geometry literature, and I haven't seen it in robotics literature either, but it's a very basic thing. I have this very simple sensor. It's one of the most common sensors in robotics, and yet no one's thought about this. The uncertainty that you get when you have measurements like that, completely characterizing this. Does that make sense? So I have this as a parameter y now. Okay, right? And I can ask questions like, what's the topology of this? Right? What's the topology of this pre-image? And how does that topology change as a function of y? Y can go from 0, right, up to, in fact, there's some critical value. What is that? Well, what is that? Is that a well-known definition of a polygon? What's the largest distance I could measure in this polygon? Is that the diameter of the polygon? Is that right? So, well, I thought the diameter is like if I slice it with a line, right? That's not the diameter. That's not the same, right? So, I think. Let me see. The diameter of a polygon would be what if I, I don't know what it's going to be for here, but maybe if I, do some slice like that or something. I mean, it should be like that, right? So, what I'm saying, if I put a robot inside here, what's the biggest distance measured? That means I sweep along. Okay, I get it now. I sweep along the boundary, right? And I look for the largest distance I can get. And it's not going to be that, though, right?
It must stay inside the polygon.
That's right. It should stay inside, right? So okay. So it's bounded above by the diameter, right? And it's probably not too hard to compute. Oh, that sounds like those functions that people are computing for the part orienting and those kind of things. Right? Yeah, that's right. So that's nice enough. So that's one very simple thing. So there's a range of values from 0 up to that, whatever that is, some diameter-like thing, right? And then I want to know inside of that interval, how does the topology of this change? What is the structure of that? Anyway, if anyone has any ideas about that, I would love to talk about it. I think it's very interesting.
But
So, yes?
I think it must be on the vertices, on the some